Welcome. We're going to be looking at analytical approach and properties of limits as x approaches positive and negative infinity. So we're going to look at some properties, and we're also going to look at a couple specific rules and properties. Namely, we're going to be looking at the limit of 1 over x, and we're going to be looking at the sandwich or squeeze rule, squeeze theorem, applied to limits as x goes to positive or negative infinity. So let's go over some properties, and the nice thing is that the same properties apply for limits as x approaches positive or negative infinity as they did when x approached some finite number. So we're just applying things we already know to new limits. So if L, and these are in your notes, and there is one thing I'm going to add coming up that I want you to add to your notes, but you don't have to write a whole lot, so you can add one little thing for me, right? So if L, M, and K are real numbers, and the limit of f of x as x approaches positive or negative infinity is L, and the limit of g of x as x approaches positive or negative infinity is M, then according to the sum rule, the limit of f of x plus g of x as x approaches positive or negative infinity is equal to L plus M. In other words, the limit of the sum of two functions is the sum of their limits. So we could just take those limits individually and add them together, and it would be the same thing as if we added the two functions and then took the limit. And likewise, we have the difference rule. So the limit of f of x minus g of x as x approaches positive or negative infinity is L minus M. So the limit of a difference of two functions is just the difference of their limits. Right? So we can find each limit separately and just subtract. Product rule. So if we have the limit of a product of two functions as x approaches positive or negative infinity, that's just equal to the product of those limits. Right? So we can find each limit separately and multiply them together. If we have a constant multiple, a scalar multiple, we can simply find the limit of our function as x approaches positive or negative infinity, and then multiply by that scalar multiple. So the limit of a constant times the function is the same thing as the constant times the limit of the function. Quotient rule. Right? So if we have the limit of a quotient as x approaches positive or negative infinity, that's just going to be, we can find each of those limits and just find the quotient, because the limit of a quotient of two functions is just the quotient of their limits, provided the limit of the denominator is not 0, right? Because that's going to be undefined. And I have got, I think, one more. So if r and s are integers and s does not equal 0, then the limit of a function raised to a power is, as x approaches positive or negative infinity, is just that limit raised to the power, provided that the limit raised to the power is a real number. Right? So the limit of a rational power of a function is the power of the limit of the function, provided it's a real number. So in other words, if we had, so let's say the limit, let's say we have f of x we have f of x raised to the 1/2 power, right? And let's say L here, the value of the limit, is equal to -6, right? Well, that would be a problem, right? Because if we were to take the square root of -6, right? Because 1/2 power, 6 to the 1/2 power, right, is the same as the square root of -6. That would be a problem, right, because this is a complex number and not a real number. Right? And all of our limits are going to exist in the real numbers system, not in the complex number. So this would be a problem. Right? So long as you don't have something that would be a problem, like a square root of a negative number, or taking the log of a negative number, or anything that just wouldn't work, right? Then it's fine. You can just take the limit and raise it to the power. So let's look at some examples. And so I added some that I want you to put in your notes. I added them after I created your notes, realizing I need to have some applications of our properties. All right, so just want you to write these down. Pause me if you need to. And then we're going to write all of these formally, and so I want you to write them formally as well. So we have the limit as limit of f of x as x approaches infinity is equal to 10. And we have the limit of g of x as x approaches infinity is equal to 5. Now I decided to make it infinity. I could have made it negative infinity. So long as they both were the same. If they're headed two different ways and we're taking a limit to different things, well then I can't combine them. So we have to be taking the limit as x approaches the same thing. I'm just moving these over so just to make sure I have enough space here. All right, so we want to find the limit of f of x plus g of x as x approaches infinity. Well, that's just going to be equal to the limit of f of x as x approaches infinity plus the limit of g of x as x approaches infinity. And we know those two limits. The limit of f of x as x approaches infinity is 10. Limit of g of x as x approaches infinity is 5. And so the limit of that sum is going to be 15. The limit of f of x minus g of x as x approaches infinity is just going to be equal to the limit of f of x as x approaches infinity minus the limit of g of x as x approaches infinity. So the limit of a difference is just the difference in the limits, and so that's just going to be 10 minus 5, or 5. The limit of f of x times g of x as x approaches infinity is just equal to the limit of f of x as x approaches infinity times the limit of g of x as x approaches infinity. And so that's just going to be equal to 10 times 5, or 50. The limit of g of x divided by f of x as x approaches infinity is just going to be equal to the limit of g of x as x approaches infinity divided by the limit of f of x as x approaches infinity. Right? And so that's just going to be equal to 5 divided by 10, which is 1/2. And finally, the limit of 7 times g of x as x approaches infinity is equal to 7 times the limit of g of x as x approaches infinity, which would just be 7 times 5, or 35. All right, so there is some practice with applying properties. And I actually have a whiteboard practice for you where you can apply these same properties. Right? So if you need to, just pause the tape so you have a chance to write these down. Right? And we're going to look at 2 more things in this particular podcast, and they're both in your notes. Right? So let's look at the first one. Little rule that we're going to need to learn to be able to use a sandwich rule. And that is evaluating limits as x approaches positive or negative infinity. So if we have the limit of 1 divided by x as x approaches positive or negative infinity, that's going to be equal to 0. And the way I like to think of it is, if you had one cake and you kept cutting it up into an ever-increasing number of pieces, how much cake are you really going to get? Well, you're not going to get any cake. You're not even going to have a crumb. Right? Because you've cut them up into so many pieces, and you're not going to stop. You're just going to keep cutting them. And when you've cut it all up into crumbs, you're going to cut it up some more. Right? So that limit is going to be equal to 0. We can also think about the function y equals 1 over x. Right? And remember that as x gets larger and larger, right, it heads to infinity, or gets smaller and smaller, heads to negative infinity, that function heads closer and closer to y equals 0. So all other limit laws from before are also true, and now we have one more that we can add. So it doesn't have to just be 1 over x. If we have the limit of c of x, c divided by x, as x approaches positive or negative infinity, and c is any constant, that also is going to be 0. Right? So even if you had 5 cakes or 10 cakes, if you keep cutting them up into an ever increasing number of pieces, never ever stopping, you're still not going to get any cake. Right? So if a numerator stays the same and a denominator grows without bounds, the limit of f of x as x approaches positive or negative infinity is going to approach 0. It's going to equal 0. Right? So I have this in your notes, and we're going to use this principle with the sandwich rule, and we're going to apply it to the limit of a specific function. So let's take a look at that function. All right, so in the next example, so f of x is going to be the quotient of a sine or cosine expression. Specifically, we're going to be doing a sine expression and a polynomial. And the idea is that we've got something bounded by something approaching positive or negative infinity will also approach 0. Right? So you can add this in your notes if you'd like. It's just kind of in symbols, the same thing we have here. So the limit of form of something bounded divided by something increasing or decreasing without bounds is going to approach 0. In this case, let's take a look at we have our something bounded, and that's sine x. So we need to bound sine x. And we're going to use the sandwich theorem for this. All right, so the sandwich theorem we visited. The sandwich theorem also holds for limits as x approaches positive and negative infinity. Right? And it works very nicely with sine and cosine, right? Because of that fact that it oscillates between -1 and 1, right? It doesn't go beyond those points, right? So if you multiply something by sine, right, you're going to either keep it the same or make it smaller. So of course, in this one, we're going to assume x is greater than 0 because we're taking a limit as x approaches infinity. This, by the way, is in your notes. I did add on the side there the steps, and you should add those as well to your notes somewhere. We'll add them one time. We're going to do the same steps for both of these, and we've got f of x equal, we're going to find the limit of f of x as x approaches infinity and as x approaches negative infinity. All right, so let's take a look at using the sine rule. At using the sandwich theorem to find this particular limit. All right, so our first step is we're gonna bound sine x. We know that sine x is always going to be greater than or equal to -1, and it's always going to be less than or equal to 1. All right? So now we're going to divide all 3 parts by x, and here our x is greater than or equal to 0, or x is greater than 0, and the next one is going to be less than 0. So the middle part is going to be our function here. So we're going to divide this one by x, and this one by x, and this one by x. And we know that sine x over x is going to also be in between our 2 functions, -1 over x and 1 over x. So now we're going to apply the squeeze or sandwich theorem. All right, so we've got a function that is greater than or equal to these 2 other functions for an interval. And now we're going to take the limit of each of our 2 outside functions, right, that is bounding our inside function. So we're going to take the limit of -1 over x as x approaches infinity, right? And so if you have any constant, and it doesn't matter if it's positive or negative, the limit as x, and you have that constant divided by x, right? The limit as x approaches infinity is going to be 0. The sign is immaterial. If you have a constant, something bound by something growing without bounds, your limit is going to be 0. So now let's take the limit of the other side. The limit as x approaches infinity of 1 over x. Oops. I don't know what happened to my x there. Well, we just went over that one. That one is also 0. All right, so notice here you have a function that's bound between 2 other functions. And the limit of those 2 outside functions as x approaches infinity is equal to 0. I'm going to give myself a little more space because I can. Oops. I don't want to insert a blank page. I want to clone this page. And I don't want spinning ball of death. I think we have cloned it successfully. Yes. So I'm realizing that I'm running out of space. So I'm going to get rid of this. Oops. Cut. And then we'll continue with our limit. Cut. There we go. All right. So now we always need to justify with the sandwich theorem. Right? So since negative 1 over x is less than or equal to sine x divided by x is less than or equal to 1 over x, and the limit of negative 1 over x as x approaches infinity is equal to the limit of 1 over x as x approaches infinity by the sandwich or squeeze theorem. The limit as x approaches infinity of sine x over x is equal to 0, 2. And there we go, right? So we have found our limit using the sandwich rule and justified it. Right? So now let's do one more. And this time it's going to be as x approaches negative infinity. Same steps. And we're going to get rid of all the things that we don't need anymore because they were on the other page. And come on. I should have anticipated that I was not going to have enough space. There we go. Let's get rid of this. Cut. We'll leave the side up there. Now we can just get rid of this. Whee! All gone. And we're going to move this up. So just like before, we know that sine x has to be less than or equal to negative 1 and greater than or equal to 1. Right? And now we're going to divide everything by x. The only thing is that x now is getting is a negative number, right? It's decreasing without bounds, right? So we have a little bit of a problem here, right? So if I plug in a negative number, right, because it's as x approaches negative infinity, let's say I plug in a negative 5 there, right? And I plug in a negative 5 here. So is that those negatives are going to cancel. Is 1/5 really smaller than negative 1/5? So we do have a little issue here with our inequality. So because x is negative, remember what happens when you multiply or divide an inequality by a negative number? We have to switch the direction of the inequality symbol. Just a small thing we have to add, but we don't want to be saying something that's not really true. Right? So in this case, negative 1 over x is actually going to be greater than or equal to. Right? So before, we're going to leave the x out so that we're not saying something that's untrue right now. And we'll just switch the inequality sign. So now we have negative 1 over x is greater than or equal to, sorry about that, sine x over x is greater than or equal to 1 over x. All right? And now we're not saying something that's untrue, right? So now we'll find the limit of negative 1 over x as x approaches negative infinity. Right? Doesn't matter whether you're approaching positive infinity or negative infinity. If you have a constant divided by something that's increasing or decreasing without bounds, the limit is 0. Okay? And so the limit as x approaches negative infinity of 1 over x is also 0. So now we know what the limit of sine x divided by x is as x approaches negative infinity. Right? So we have negative 1 over, actually I'm going to reverse the order I write them in. That way I can write the inequality symbols. I kind of like to write them this way. Right? So 1 over x is less than or equal to sine x divided by x, which is less than or equal to negative 1 over x. And I'm going to kind of note that as x approaches negative infinity. Right? I probably should have back here. We don't really think about it when I don't have to change the inequality signs. So we'll just leave this one as is, but we'll make a little note there as x goes to negative infinity. We had to reverse those, the direction of our inequality. And the limit, and I really should add the word since in here so I can make it as a sentence. There we go. Everybody move over. Oh, except for, there we go. Since, I'm going to move this. There we go. Since 1 over x is less than or equal to sine x divided by x, which is less than or equal to negative 1 over x, as x approaches negative infinity, and the limit, actually I'm going to run out of space over here. I'm going to just move down one row, and the limit of negative 1 over x as x approaches negative infinity equals the limit of 1 over x as x approaches negative infinity. Then by the sandwich squeeze rule, sandwich squeeze theorem, whoops, an odd little break in my word there. I really should have, I gave myself extra space and I still wrote too big. Theorem, we can squeeze it in, I can do it. The limit as x approach, well, now I just made the thing move. As x approaches negative infinity of sine x over x equals 0 too. There, we've done it. All right? And we use the sandwich theorem, sandwich squeeze theorem to prove our limit. And I'm just making that a little nicer looking. There we go. All right, so here you see how to apply something we've learned, which is the limit of 1 over x as x goes to positive or negative infinity. And the sandwich rule, something we learned earlier. Spacing here is really just bothering me. I'm just trying to make it look nicer. And so we saw how we can apply that sandwich rule to find the limit, not only as x goes to 0, but also as x goes to infinity or negative infinity. Right, so we're going to be learning some different ways to analytically determine limits as x approaches positive and negative infinity. All right, so bye for now.